Hello, Math Studies students, and welcome to your online lesson. Today we'll be continuing discussions about statistics, but specifically we'll be talking about something known as the chi-squared test for independence. The chi-squared test is a test that allows us to determine if two variables essentially are affecting each other or if they are truly independent, having no effect on one another. We will know we are successful when we can use the chi-squared test to obtain a value of chi-squared. And eventually we'll be using this to interpret more data, but for now we're just focusing on getting a chi-squared value, and we'll talk about what to do with it next. Now, again, it's chi-squared, even though it's spelled C-H-I, it is not chi like chai tea, it is chi like the beginning of the word kite. Let's talk about what chi actually is. So chi-squared, we can see, is it's a Greek letter, and it looks a little bit like an X. And in fact, the whole reason we use X in math classes have to do with the fact that it originally came from this value chi. Now, when I draw a chi, I make it a little bit more exaggerated. So I put sort of a hook like that, and then I draw a large line there, as opposed to just drawing a regular old X like that. So we want to exaggerate it a little bit, and it's squared, just like a squared number where we have an exponent of 2. It looks at our data and decides if we have two variables or two classifications that are independent. Now, this chi-squared is equal to this formula here. And we start off with a sigma, capital sigma, which in math class always means the same thing. Sigma means sum when it's a capital. So we're going to add up all of this stuff right here. And this stuff is, I'm taking my observed frequencies, and we've talked about frequencies before in statistics. It's how often something occurs. And we're going to be subtracting our expected frequencies, and we'll talk about how to get those expected values. We'll be squaring them, dividing them by the expected value, and then doing that for every single piece of data that occurs. And then when we are all done with that, we're going to total it up using the sigma. So what does that look like? It's not going to look like a traditional math problem per se. It's going to be a little bit different. And so we'll jump right in essentially to an example. So here is an example problem. We have a table that shows the results of a sample of 75 randomly selected students classified according to gender and amount of sleep each night. So those two things in italics, gender and amount of sleep, are our two variables. And again, they're variables because depending on who you ask, they may have a different gender and they might have different numbers of sleep that they get each night. And so we can see that there were 75 total people participating in this. Now, of those, we had 42 that were female. We had 33 that were male. We can also see that we had 28 people who got at least 8 hours of sleep, meaning 8 or more hours of sleep. The least would be 8. And then we have 47 who had less than 8 hours of sleep. And so we've got all of these different classifications going on. The amount of sleep, more or less than 8, and then whether we're male or female. And we're counting up the amount of each of these things. So again, we can see here there were 12 males who got less than 8 hours, or at least 8 hours of sleep, and were male. Here we have 26 females who got less than 8 hours of sleep. Again, a total of 75 people. In the outer regions, we have all these totals right here. And that's really what we're going to be focusing on. Now, on the previous slide, we talked about two different things in our formula. F sub O, which was observed data, and I'm saying F sub, like a submarine, F sub O, because it's a little subscript, sort of the opposite of an exponent, which is tiny and high. This is tiny and low. And then we have, again, F sub E, which is our expected data, which is not anywhere on here. So what are our observed data? Well, we observed or recorded that there were 12 males getting at least 8 hours of sleep, and there were 21 more males who got less than 8 hours of sleep, for a total of 33 males. But 12 and 21 were the observed frequencies, or the observed data. And then for females, we had 16 of them getting at least 8 hours of sleep, and then 26 of them getting less than 8 hours of sleep. So 42 different females were observed, and those are observed values. So for this table, we only have 4 observed pieces of data. Well, what I'm going to do now is I'm going to clean this up and get myself some more space here on the screen. And the first step for chi-squared is I'm really going to copy this exact same table over. So you can watch me do that here. So what did I have? I had 4 rows and I had 4 columns. The bottom ones were sums or totals. And then I had my male, I had my female, and I had a grand total of 75 participants. Here was at least 8 hours. Here was less than 8 hours. And so that's my little quick setup. And this is called an expected value table. So expected values, also known as F sub E. This original table was our F sub O. This is going to be our F sub E table. All right, so what I'm not going to copy over is any of these observed pieces of data. All I'm going to copy over are the sums. So I'm going to put a 33 here, a 42 there, and again, those just came from the sums on my original table, and then I'm going to put a 28 and a 47 here. What I'm not copying over at all are those original observed values that I still have circled. The number of males who got at least 8 hours of sleep, the number of females. I know the total number of males, I know the total number of people who got at least 8 hours of sleep, but I'm not putting down the specific individual values. Now, to actually get those values, what I'm going to do is I am going to take the row total times the column total and divide it by the grand total. So what I mean by that is right here in this first box that I'm circling, let me circle it in red so we know exactly what we're talking about. Well, we have a row, the male row, which has a total of 33. So I'm going to take 33, and then we have a column, which has a grand total of 28, and I'm going to multiply those two together. So I'm going to have 33 times 28, and then I'm going to divide that all by the grand total of 75. And a calculator is going to be really helpful here. And I'm going to get 12.32. So I'm going to try to squeeze that in right here. 12.32. All right. And now I'm going to get this next value, which is the male and the less than 8, which is going to be this box right here. So I look for the row total, which is still 33 because there were 33 males, and then the row or the column total, which was 47 this time. So 33 times 47, divide all that by 75, and I get 20.68. Again, where did that 20.68 come from? I multiplied the row total times the column total and divided by the grand total of that particular value, which was the males and less than 8. Okay, now I'm going to do the same thing for the females here. I'm going to look at their greater than or equal to 8 column, which we would be looking at this box right here. And I'm looking at the row total being 42 now because there were 42 females, and yet there were 28 people who got at least 8 hours of sleep, and still dividing that by the grand total of 75. And I get 15.68. And now I'm going to do the last one here, which is female and those who got less than 8 hours of sleep. So our row total for the females is still 42, but now our column total is this one right here that we're trying to fill in, and that's 47. So I have 42 times 47, all divided by 75. And for this one, I get 26.32. Those are our expected values. Now, the expected values are the ones with the decimals in it right here. It's not the sums, but I used the sums in order to find those expected values. Now, the other interesting thing you may notice here is if I go to this first column here, and I take the 12.32 and the 15.68, if I add those together, I still do get a grand total of 28. And if I go to the next column with the less than 8, and I take the 20.68 and the 26.32, and I add those together, I still get 47. And I could do the same thing with the rows, adding the male row together to get 33 and the female row together to get 75. So those are my expected values. Now the question is, what do I do with them? Well, I'm going to make a table that will allow me to do our equation. And our equation said that chi squared is equal to sigma, or the sum of my expected data, or my observed data, F sub O, minus F sub E, my expected data, squaring all those things and dividing by my expected values. That's a lot of stuff I need to do for each and every one of these numbers. So what I'm going to do is I'm going to make a 5-column table. So I'm going to have f sub o, my observed data, f sub e, my expected data, f sub o minus f sub e, f sub o minus f sub e squared. Finally, I'll take all of that, the f sub o minus f sub e, quantity squared, and I'm going to divide it by f sub e. And I say this is a table because I'm going to do each of these steps separately, kind of like this. So f sub o, those were the original values. I still have them circled in blue up here on my original table. So I like to go first row straight across. So I have 12, then I have 21. That was my first row with my males. And now I'm going to the females where I had 16, 26. So just like I read a book, I'm going left to right, top to bottom. Now I'm going to do the same thing, but I'm going to do the expected values. Again, I don't care about the sums. I only care about those ones with the decimals that we calculated. So I'm going to have expected value that corresponds to this 12 up here, but now it's this 12.32 down here. So I have 12.32. And then for the expected values that corresponds with my original 21, it was 20.68. And then I had the next row, which was 15.68. And finally, 26.32. All right, now we go to our next column, and it tells me to subtract those. So I'm taking 12 minus 0.32, so it's negative 0.32. Now I'm going to the next one, which is 21 minus 0.68, which gives me a positive 0.32. And then I go to my next one, which is also a positive 0.32. Again, what am I doing? I'm taking this column, the value in it, subtracting that one. So I took 16 minus 15.68. And then finally, 26 minus 26.32, which gives me negative 0.32. And you'll see there's sort of a pattern here where I had positive and negative values. And that's occurring because we have so few data points. When you deal with larger numbers, you will not necessarily see a pattern like that. Now the next step is I want to take what I had before, f sub o minus f sub e, but now I'm squaring it. So to square it, I'm just taking the number times itself, including the negative. And a negative times a negative will always be a positive. A positive times a positive will always be a positive. So regardless of whether I had negatives in the third column, I should not in the fourth column. And so when I square them, I get 0.1024. Since all of these numbers are either 0.32 or the opposite of 0.32, negative 0.32, they're all going to give me the exact same value. Again, this is a fairly simple example with few data values, few rows, few columns, and so you won't always see this happen, but it's certainly happening here. And now my last step is to take everything I've done so far, the f sub o minus f sub e quantity squared, and then I'm dividing it by the f sub e. You might say, well, I have the same values already for everything, so I must have the same values here. But you'll notice that my f sub e column, which is the second column right here, has a different value for every single row. So I need to do each of these separately. And I'm going to pause the video and do all this math, and so that you can just see that jump in. All right, and so I've got all those values now. And again, where did I get them from? I took my fourth column, which was my f sub o minus f sub e squared, and I divided it by my f sub e, which was my second column. So I just took 0.1024 and divided it by 12.32 to get the 0.008312 in that first row. And then I took the 0.1024 and divided by 20.68 to get the next one, and so on and so forth. Now we're getting so close. We have to go back and look at our formula. What does chi-squared say? Chi-squared is equal to the sum of this stuff. The data, or observed data, minus the expected data, quantity squared, all divided by the expected data. And I did that all for all four pieces of our rows and columns, essentially. But now we have to do the sigma part, which again means add it all up. So I only have four numbers. I've got the 0.008312, the 0.004952, the 0.006531, and the 0.003891. And I'm going to add all those together. And when I do that, I get 0.0237. And that is my chi-squared value. And that's where we're going to stop for this lesson. So again, I just added these all up right here to get chi-squared is equal to this value, 0.0237. Now, what does this mean? Does this mean they're independent? Does it not? That's going to be saved for a later video. I just wanted to go through the actual process here. So hopefully we have a little better idea of how to calculate chi-squared doing all this work by hand, and we'll talk more about this next time.